Greetings to those interested in learning about confidence intervals. After watching the first 3 videos, you should be comfortable with the concepts of the sampling distribution of sample means and the central limit theorem. Now let's think about estimating the population mean mu. If the population is too large or too difficult to access, and it is nearly impossible to calculate the population mean mu, how can we estimate this value, and how accurate is our estimate? We learned before that x bar is a good estimate of mu, but we also learned that if we took more than one sample, we would get different values of x bar. We imagine graphing these different values of x bar to build a sampling distribution. However, we know that in reality we would only obtain one sample from the population. How can we use the one sample mean we found to make inferences about the unknown population mean? Pause here to think about this. To determine an answer, consider the following situation. What if we were interested in estimating the average height in inches of adult males in the state of Virginia? We know it will be extremely difficult to determine the population mean height because it would be nearly impossible to measure every adult male in the state of Virginia. However, something that is feasible is to take a simple random sample of 36 adult males in Virginia, measure each man's height, and calculate a sample mean. I need to consider 2 assumptions before continuing. I will assume the population standard deviation value sigma is known to be 3 inches. This is somewhat unrealistic. We will soon deal with situations where the population standard deviation is unknown, but remember, this is just an illustration where we build a new idea based on concepts we already understand. The second assumption is that the central limit theorem properties hold in our example. Do you think this assumption is reasonable in this example? Pause here to think about it. Though I may not know the shape of the population distribution, in general the shape of the distribution of heights of one gender is known to be approximately normal. Even if we did not know this, our sample size of n equals 36 is large enough to consider our sampling distribution of sample means to be approximately normal. In contrast to the first assumption, this second assumption is realistic. Let's go back to our sample of 36 men. These values are the 36 heights in our sample, and our sample mean x bar is 68.5 inches. This is one possible estimate of the population mean, and again, we know that if we took a different sample, we would obtain different heights and a different sample mean. Now, think about the concept of sampling distributions. What do we know about the center and spread of the sampling distribution of mean heights? Pause here to answer this. Well, we still do not know the population mean mu. What we do know is that the sampling distribution of all possible sample means is centered at mu, and we know that the standard deviation of the sampling distribution is sigma over the square root of n. In our example, this value is 0.5. Since we do not know mu, we do not know where our x bar of 68.5 is located on the sampling distribution in relation to mu. Watch as I show that x bar can be located anywhere on this sampling distribution. Pause here to reflect on this idea. Since we know that the sampling distribution is normal, we can say that if we go 2 units of standard deviation away from mu in each direction, that approximately 95% of the sample means fall in the area shaded in red. Pause here to recall this property of the normal distribution. Based on this property, we know some information. There is roughly a 95% chance that the unknown population mean is no more than 2 standard deviations from this x bar. This is because about 95% of the x bars fall within 2 standard deviations from mu. Remember, the values along this normal curve are all sample means. Thinking about it in a different way, if we reach out 2 standard deviations away from my sample mean x bar on both sides, we are roughly 95% sure that the unknown population mean will be captured in this interval around a specific x bar. Let's visualize intervals we generate from various locations where x bar can fall relative to the unknown population mean mu. Notice that most of the intervals capture the mean, but not all of them. Now let's look at this situation using numbers. Remember, our sample mean is 68.5 inches, Again, we are not sure where 68.5 is located on this distribution of sample means because we do not know mu. For example, let's say 68.5 is here. To more accurately and confidently estimate mu, consider the fact that there is an approximately 95% chance that mu is no more than 2 standard deviations, or 1 inch, from our x-bar of 68.5. So we can construct an interval 67.5 to 69.5 by adding and subtracting 1 to and from 68.5, and we will say that we are roughly 95% sure that this interval captures the unknown population mean height, mu. Remember, this interval could actually be here, or here, or here, or any other location. This interval we just constructed is called a confidence interval, and this interval supplements our estimate of mu with an indication of x-bar's variability. Here is the structure of the formula. The 2 in the formula will change depending on the level of confidence you want. We have stated that we are roughly 95% sure or confident that the interval we constructed contains the population mean height. In our example, the confidence level is the 95%, and that percentage can and does change depending on how confident one wants to be in their interval. We use 95% because it was a familiar value based on a property of the normal distribution described earlier. Note that it is also the most common level of confidence. Now, when using a standard normal distribution, approximately 95% of the data will fall within 2 standard deviations of mu, or plus or minus 2 units from 0. Pause here to calculate the exact standard normal values where exactly 95% of the data fall between these two values. Again, using the standard normal distribution, exactly 95% of the data fall within 1.96 standard deviations of mu, or plus or minus 1.96 units from 0. See the picture of the standard normal distribution. Now see the formula for the 95% confidence interval. 1.96 is called a critical value. Now suppose we want to be 99% confident. What does this mean, and how would this affect the calculation of the confidence interval? Pause here to think about this. First, 99% confident means we will be 99% sure that our interval will capture the true population mean. To obtain the standard normal critical values, it looks like we'll need to do another calculation. Will these standard normal values be bigger or smaller than plus or minus 1.96 in absolute terms? Pause here to calculate these values. We discovered that the approximate standard normal critical values are plus or minus 2.575. These critical values are labeled z-star in our formula. See our general formula for the confidence interval with any confidence level. Below it are the formulas for the 95% and the 99% confidence intervals. The part of the formula to the right of the plus or minus sign, circled here, is called the margin of error. Now pause here to calculate the 95% and 99% confidence intervals for our height example. I have displayed the 95 and 99% confidence intervals for our mean height example here. What do you see? Pause here to think about it. I will address these what happens when type questions in the next videos. Again, the correct interpretation of a 95% confidence interval is that we are 95% confident that the interval we constructed around our sample mean captures the unknown population mean mu. We do not know exactly what the true mean height is, but we are 95% confident that the interval 67.52 to 69.48 contains the true mean. In the next video, we ask the question, what would happen if we took many samples and constructed many confidence intervals? We will simulate what happens, and this will help us gain more understanding about the interpretation of a confidence interval. Also, we will find out what happens to the margin of error and the width of the confidence interval as the confidence level and the sample size change. Thanks for watching.